Yes, and I can start by mentioning that this work has also been published by now. You can find all the details of this work in the article. The background and motivation for this work, which is about crowding and predicting crowding, is that we know the negative sides of that crowding has on traveler satisfaction, comfort, reliability, and so on. And as the public transport systems get more utilized, we need to use the capacity that we have more efficiently. And at the same time, we have new data sources emerging, like automatic vehicle location, automatic passenger counting, and automatic fare collection data that allow new systems for example, providing real-time crowding information. And this is something that's now emerging mostly in train and metro systems, but also we're starting to see them in bus systems around the world. And information like this can allow travelers to make better informed decisions, whether to board a vehicle or maybe wait for the next one, if that seems to be less crowded. Maybe select a train car that's less crowded, based on how the individual values crowding versus walking and waiting and so on. Of course, in order to provide accurate real-time crowding information, we need to be able to predict the crowding that will be inside the next vehicles that arrive, if we have a traveler waiting at the stop, for example. It's not only sufficient to report the current crowding in that vehicle if it's several minutes and many bus stops away. And the other thing that has motivated this work is that the information should be relevant to the traveler, and that, of course, both in the sense that it should be up to date and accurate, but also in terms of what crowding metrics that we provide to the traveler. And there I argue that just providing some indicator of number of passengers on board the vehicle when it arrives might not be what is really interesting for the traveler. So the contributions in this work is to develop a framework for providing more personalized and predictive crowding information based on inputs from the user, like the time of the trip, which could be right now, the origin stop and the destination stop, based on automated data sources, location and passenger counting data. And I consider 3 different crowding metrics that all take into account seat availability inside the vehicles. The simplest one is the probability of getting a seat on boarding. That can be very crucial for some passenger categories, that you are able to find a seat. The second one is the expected travel time standing. So how long you have to stand until you get a seat or until you alight. This metric takes into account not only where you board, but also where you are going to alight. So it's more personalized than the first one in that sense. Then the third metric is the expected excess perceived travel time, standing or sitting, I mean with this one. So that takes into account how the passenger perceives the crowding inside the vehicle, depending on if the passenger is sitting or standing. So that also takes the whole trip into account, but furthermore takes this subjective valuation of crowding into account, so even more personalized in that sense. And I've used 2 methods for crowding prediction. I will only discuss the first one today, the lasso regularized linear regression. And I have looked at how this prediction performance looks for different levels of data availability. If you only have historical data or also real-time AVL data, and finally also real-time APC data for different time horizons. So going a little bit into more specifics about the approach, I'm using a probabilistic seat allocation model since we cannot look inside the buses with these data sources. I make some simple but usually reasonable assumptions that all seats are occupied before passengers start standing. Sitting passengers are guaranteed a seat until they alight, and standing passengers are prioritized over boarding passengers when empty seats become available. And we can compute this probability of sitting or standing for a given passenger based on data on the loads and alighting counts, or in terms of boarding counts, alighting counts, or any combination of these two will work. So we have the three crowding metrics: probability of seat upon boarding, expected travel time standing, and finally the expected excess perceived travel time, which you can see defined a bit more precisely here, assuming that we have some discrete levels of crowding, and for each level we have a time multiplier that captures how much worse the passengers consider traveling in those crowding conditions compared to nominal uncrowded travel time, also depending on if you have a seat or not. So this is a real example of how this works. This is a bus line in Stockholm, and assuming a traveler that boards at stop 18 and then wants to alight at the end stop 31. The red line here in the diagram shows the load on board. So the bus is very crowded when it arrives to the first stop. Then the load on board successively goes down. But upon boarding, we see that the seat probability, the solid black line, is 0. So there is no chance of getting a seat upon boarding. But gradually, the probability of getting a seat increases as people alight along the trip. And at some point, it reaches 100%. And similarly, we see the cumulative travel time standing gradually goes up until you are certain to have a seat. And similarly, the cumulative excess perceived travel time gradually increases along the trip. So this framework for computing these crowding metrics works like this. We can consider a traveling waiting at some stop along the line. We may have historical data from crowding at this stop, historical APC data. And we might have real-time AVL data where the next buses are along the line, and possibly also information about the current passenger loads on these buses. All this information goes into the prediction models, which I will describe in a minute. Based on the predicted loads and alighting counts, we compute the probability of having a seat, and we compute these three crowding metrics based on that. Then we can do a bias correction, which I'll also come back to in just a minute. And then that will be our, finally, what the predictive crowding information. So I want to emphasize here that for at least the second and third crowding metric, it's not enough to predict the load on board the bus when it arrives to the stop where the passenger is waiting, but we actually need to predict the load and alighting counts for all subsequent stops until the alighting stop of the passenger. So here I mentioned I used a linear regression model for the prediction of the loads and the alighting counts. And I have 3 sets of predictors, some based on historical load data, taking into account average load based on the time of day, the weekday, the month, etc., and also the alighting counts. Then we have predictors based on real-time vehicle location data. And here I've used the total travel time of the bus up till the most recent stop, and also the headway to the bus in front at that stop. Because the headway can be a proxy of the load inside the bus, since we know that if the headway is long, then there are likely more passengers boarding that bus. Versus if the bus is very close to the bus in front, we can probably expect a lower load on that bus. And then finally, we have real-time automatic passenger count predictors. And there I've used the latest load inside the bus for the most recent stop. Also the alighting counts at a number of the most recent stops and the boarding counts at those stops, as well as some quadratic terms. And since I've used lasso regularization here, a lot of the parameters in front of the predictors will be 0 if the effect is not significant. So only the most significant predictors here will be finally included in the model. And then to predict these 3 crowding indicators, I simply input the predicted loads and the alighting counts into the equations for the crowding metrics. And in that way, I obtain a prediction for the crowding indicator. For the metrics 2 and 3 here, I also apply a simple bias correction, since this method creates some nonlinear effects. We can correct a little bit to avoid bias in the predictions. So I have applied this framework to bus line number 4 in Stockholm. It's the busiest bus line in Stockholm, about 12 kilometers long, 31 stops. I've considered in the direction from north to south here. It takes about 60 minutes on average from end to end. And the line runs with around 5 minutes headway, and the buses have 45 seats. We have around 30,000 boarding passengers per day and per direction. And I've used data for the afternoon peak, 3:30 to 5 p.m. using weekdays only, from data from 2016. So I have in total almost 6,000 bus trips, of which 1,200 have APC data, which can be used in the predictions. So I divide this data equally into a training set and a test set. And to compute the third crowding metric here, I used the time multipliers from Wardman and Whelan. And then I test 3 levels of data availability and the impact on prediction performance. So the first case is when we only have historical data. And the second is when we have historical load data as well as real-time vehicle location data. And the third is when we have most information. We also have real-time passenger load data. So I've looked at how much do we gain for each additional source of information. So this is how the crowding looks like along the line. You see the stop number along the line from left to right in each figure. So we can see that the load varies a lot along the line, which is one of motivation that the current load inside a bus is not a good predictor for what the load will be necessarily when it arrives to where the passenger is waiting. Also, the other crowding metrics vary quite a lot between different stops, and also they look quite different from each other. So this is some results. First, looking at the first crowding metric, the probability of getting a seat on boarding. And these figures show the accuracy of the prediction per each boarding stop. And to the left is when we have a 10-minute prediction horizon, and to the right is when we just have 1 minute prediction horizon. So if we look first at the left here, well, at the beginning of the line, there is no real-time information that we can use because looking 10 minutes into the future, there has not yet been any bus departing along the line that we can get data from. So we can only rely on historical data. But then later on along the line, we see that having access to real-time AVL data gives an increase in prediction accuracy. And also having access to real-time passenger load data gives an additional increase in accuracy. But if we compare the left and right figure here, we also clearly see that the predictions improve significantly when the prediction horizon is shorter, because when the horizon is shorter, then the next bus will be closer to the stop, and the current load or the current situation for that bus will be actually more representative for the situation when it arrives to the stop. Similarly, we can look at the second crowding metric, the expected travel time standing. Here, the performance measure is the mean absolute error. So we can see that on the left, the mean absolute error ranges between 0 and up to 2 minutes at most. So at most, we might predict the time we have to stand 2 minutes wrong. Also here, the prediction performance varies a lot along the line. And it's closely related to the level of crowding along the line. So prediction performance is generally worst where we have the most crowding. That's where it's most difficult to accurately predict the crowding inside a given bus and whether a passenger has to sit or stand. But also here we see, when we compare the left and the right figures, that when the prediction horizon gets shorter, we have a much clearer added benefit of the real-time information. And the mean absolute errors are reduced significantly. The final crowding metric is this excess perceived travel time. And here we find that for this metric, the real-time information does not add as much value for the prediction performance as for the other two crowding metrics. And that has to do with that here the whole journey from start-stop to end-stop plays a much more important role than for the other two measures. So we have to predict crowding all the way to the end stop on the line, which means that predictions are probably not so accurate, and even if you have real-time information. The final thing I can point out is the effect of the bias correction, which we can see comparing the top row to the bottom row here on the lines. We see when we apply the bias correction in the bottom row, we have basically no bias in the predictions. And we can achieve that with almost no loss of mean absolute errors. So to conclude, we see that crowding conditions vary a lot depending on the start and the end stops of the trips. And these three personalized crowding metrics show very different spatial patterns from each other, and also from the raw passenger loads. These systematic temporal variations that we can capture in the historical load data are very useful to provide a baseline prediction. But when available, real-time APC predictors always improve prediction performance. AVL predictors can serve partially as complements to APC and partially as proxies, like the headway can serve as a proxy for the onboard load, for example. The most useful predictor with AVL data is the headway at the source stop, at the most recent stop. And with APC data, the most useful predictor is the passenger load at that stop. We saw that the simple prediction method created some bias in the optimistic direction, but we can remove this with a simple correction term. The results indicate that this personalized predictive crowding information is robust to varying levels of data availability and can provide it, I would say, with sufficient accuracy to be useful for the travelers. And it can be provided even in public transport systems where the real-time passenger load data might not be available or only partially available for some of the vehicles. Thank you. Now I'm happy to take questions.